last time we were recording like 8 channels from the ADC, and then I continued working, attaching like the amplifier for the transmitter, which sends a pulse, and then the receivers. And actually it's not working right now because I'm working on the Framebuffer. And what I want to do is, yeah, I want to use the PSRAM, which is a hassle to like code, but I think I can show you a recording. This is not what I want to show anymore. I want to show you maybe a short clip. I don't know if that... Oh, what did I do? Nope. Can I play it? Okay. Yeah, basically.
My ultrasonic phased array.
Yeah.
It's running on an FPGA now, and
Oh no!
8 ADCs on the screen. It's sampling now at
I don't know if you can hear that.
8 megahertz.
However,
Displaying the wave.
yeah. There's the audio is clicking. That's why I was that's why I didn't upload that. The problem is. Yeah. Okay, so basically I wanted to make a short of that, but unfortunately the audio was messing around. So the while I was recording, and the ultrasound was messing with the audio, so I couldn't show that or upload it without like a voiceover, and then it was too much work to do. So basically, now the problem is that I have to do some beamforming. So I have to calculate where is the beamforming pixel canvas. I can show that. So I need to convert the samples to an actual display of like convolution of all the channels on each pixel to see an intensity of if there is something, if there is an echo coming from this direction or not, or point is in space. And therefore, so that's a short update. Yeah, this ChatGPT helped me to write this code quickly, so I'm using ChatGPT to... A doxing. Oh no. So this is basically showing, just rendering an offset of the samples. The rendering here is just, I think that's the phase. The red is the phase, but basically from one array element, this would be like the sample, and one complete phase of the... No, it's not broken. It's every 256 frames it resets, because I'm currently coding the Framebuffer. So yeah, but this is like a lookup table that I need to put on the device itself. I can put it in, I think, in the EEPROM of the FPGA, and basically so I'm a little bit limited in the capabilities of the device. Let me show you what I have there. So basically, so this is... Wait, no. these are the capabilities, and basically what's inside there. There is like a user flash bits. I could use that for the lookup table of like the beam, so I don't have to calculate the square root, because, hey Christian, so we have like limit SPI, SPI flash, yeah, that's too slow, but the user flash could be okay but I'm so confused. Okay, so we need, like, if we have like the receiver and we have a transmitter here somewhere. So the transmitter sends the wave and it bounces off an object here and is bounced back. And this is basically the receiver will, somewhere here as the receivers, they will see the wave. So if you must imagine this is like a 40 kilohertz wave, so 8 millimeters is a complete phase wavelength, and they will record. Record this. I think I showed that in one of my last videos. They will record a phase shift of this echo, someone like that. Let me move over here. Something like that, and basically from the alignment of the waves, you can render like a beamform, a display where there is like a shadow here or something, which would show an object on the screen. So this is our goal, or the goal for my project, and what I determined since last time is that apparently if I want to have like 40 kilohertz is the transducer's resonance frequency. So we have 40 kilohertz frequency, kilohertz frequency, and we can sample up to 2 megasamples easily, but then we already okay, so I determined it would be nice to have like a sampling frequency of 1.28 megasamples, because if I do that, if we divide like 40 kilohertz by 128, we get 32 samples per phase, which is nice. So we get like individual readings from the ADCs, which will be 32 in total, and we can use like a discrete cosine transformation or something to determine like the amplitude here. Super easy. Yeah, we just need to like multiply with a lookup table, which I also calculated, lookup table of a sine wave, and then we can see, okay, we have a 40 kilohertz reflection here. So it's like a filter. It sounds a lot. Hey Dave, it sounds a lot, but this is what I determined, and I added this to the code, and this is what you see there. Like okay, yeah, blah blah blah. And if I hold my hand there, you can see these are like 32 samples and you can see like the 40 kilohertz. So now to calculate this, I need to redraw that. Let me redraw that. Oh. Okay, to calculate that, it's like a free course. So, it's so tiring, my talk. Okay, so we need to calculate for each pixel on this beam here. We need to calculate how far like this pixel would be. So if we have an obstacle here and it would reflect to the to the receiver, from the transmitter to the receiver, then we need this, and then we need like the sum of the path to there and the distance to back to the receiver. So, and this is basically the distance of this object would basically determine if we see like a recording of our wave, which has noise, and then we see the 40 kilohertz here, and like that. So this will be basically the distance. But how to calculate distance to time? We have 343 meters per second. That's like an average for this altitude here. Like maybe it's a little bit should be slower. Yeah, but is it slower or faster? No, it should be. Higher pressure is faster, and this should be slower. Okay, however, we can calculate basically the sample count here. But the problem is the distance is calculated like from squares here, x, y, and we calculate basically x square plus y square, which is only a multiplication. We could do that, but the problem is the square root. And square root, I mean, there are algorithms, but I can only do like iterations here. I can't do a lookup table for square root. Inverse square root, you can do like some calculations, but it gets complicated, more complicated than needed. But what I can do is I can store for, let's say, for each pixel in this beam, I can store basically a square. It doesn't need to be like the complete beam, because this could be mirrored like that. I don't know yet if I do that. I can mirror that with some logic. But I can basically store for each pixel the offset in the samples. Yeah. Yeah. But I need, at the end, I need the offset in samples here. So this is like the sample offset. Let's call it SI. And what I can store for each pixel is basically in SI. And SI for each pixel. And this won't change. And the table, since my array is like that, at the end I can basically shift the table for each sample. So for each receiver I can basically add the offset, and I will basically set the scale so the offset of these two as pixels are like a full pixel like integer. So I used, I think, 4 pixels or 8 pixels here to have between the receivers, so I have the field of view here, which is easy calculatable, and I can do basic bit operations to shift it. So a lot of thoughts during the last week and a lot of coding. Quantify what is So the problem with quantification is what will happen is that you can see, let me pick another color. You can see like for this receiver and this pixel we have the index like that. For the receiver that is next to it, this will be like more to the left. So yes, so what I will get, the problem is I will have, like, for the next receiver I will have this index, and basically what we can already we will be able to see a shadow here, which is like a little bit wavy, 40 kilohertz wave. If like we have 8 arrays summing up and they have an amplitude there, so there is like the shift is like different for each array, but it will all like be at the same spot. So at the same spot we have a different index for this pixel, and they will basically, we can add them up and we will already see something's happening here. And then if we want to make it like right, we can do discrete cosine transformation to see, okay, that's actually 40 kilohertz, and get the intensity or something. That would be enough, or discrete Fourier transform, which is a little bit harder to calculate. So, but I think the simplest way is to start like just adding the waveforms with the corresponding indices of each pixels, and then render that as an intensity. So, I need to heat it up a little bit. Wait, maybe I can show some code even. Do I have some code? Okay, here. So this is the beamforming HTML. So this is basically what you see. This is like multiples of 32, which is the phase. It doesn't align with each pixel, but basically simplest would be a peak detector with a threshold and time domain sampling, I think. Yeah, I don't know if that's best way. Yeah, you don't need like to identify it. You just visualize the sum, and that will be already okay. So this is like the lookup table that we can store in our EEPROM if we want, and this is the code. So we have basically the resolution of our screen, which I halved the resolution for the TFT, and then I have the millimeters per second speed of sound. Yeah, time of flight. And then we have the sensor count, the distance in millimeters. Then we have in pixels and sampling rate, which is our 1.28 mega samples. Then we get the maximum, we have the maximum distance for the resolution, and the diagonal is a little bit further for our table if we want to have like a 45-degree cone. So it will be a little bit further up to the corner of a square. Also, we can calculate the maximum time. Tummy is bursting. Okay, then we have the sample count that we calculate for the maximum time and so on. And this is basically the rendering. The lookup table should be output. I can show that. F12, you will see basically this is the result. So this is our lookup table basically, which is the sample index for each pixel. Then we have the distance. Distance is like that I decided 30 centimeters, which is really low, but I can elaborate on why that at some point. We need a further distance between our array elements to get like the distinction at a further distance, unfortunately. So we need a bigger array, or we can only get precise results for short distances. Okay, so this is the array we see. Then return time, it's like a 500th of a second, and that's only like 3,166 samples, and that's the bits for all arrays that I need. That's 202 kilobit, and that is still good enough with, where is our, since I want to store them in the block RAM, we can do that. That's I'm doing this already. That fits nicely in 202. We can even do like double the distance at the same precision. So, but it's only 60 centimeters if I do like double the distance. Otherwise, I can use the PSRAM if I want to, but this will be tricky because I want to use the PSRAM for a Framebuffer, which will be today's task. Oh, samples per pixel, 13.19. So, and one phase is like 32. This is what I did last time. Then we have, yes, sign table based also. ChatGPT helped me doing that. I just prototype with ChatGPT now all the time. Super easy. Oh, that's better. Some soup first and then. So now the problem that I got is that calculating the beamforming, I need to add up, grab the samples, add them all up, and render per pixel, which will be, I think if we only like do that, we can still make it like in time for each pixel on the fly, so real time without a buffer. But if we want to do more sophisticated calculation per pixel, it would be best to have a frame buffer. And the device has some RAM, which is, does it say here? as DRAM bits is only like, it's the interface. It's not the actual embedded, does it say? So there is a, I think I can't find this here. No, but this won't tell us here. Does it say the? Let me check the go-in. So products little b. Oh, come on, slow. Okay, and then we have NR. This is on the Tang Nano. And what it says, it has embedded PSRAM bits. No, that's NN4, 64 to, that's like 64 megabit, which is a lot, but it's PSRAM. So it's not like, how that looks like is, we have like the FPGA IC, and let's say this is like the FPGA, and there is like a, I think that there are even like two. So there are two PSRAM dies included in that IC, which are like wired to the FPGA. So we have to treat it like, somehow like treat it like external ICs with a bus, and not like internal like the other block RAM or whatever. Block RAM is inside, like on the die. This is block RAM, and this is like the PSRAM. So here we go. Now the problem with the, I lost like 1 day of trying to find out how PSRAM works. I can show it shortly. I'm still not like I didn't figure it out completely. I can show you an example how that looks like. So the problem with the go-in stuff is that nobody, it's a quite fresh device, and nobody did a lot of work on that. So basically the PSRAM, we need to, by the way, I updated to the full version, not the educational version. You can get a free license from Go-in. So we need to do a soft IP core, and there is basically a PSRAM memory interface. And what it says is that's also for embedded win-bound PSRAM. And if you open that, it says already it's up to memory. Oh wait, this one is up to 250. Okay, this is new for me. Okay, I'm using it at. Let me check that. Is this all right? Okay, yeah. So I can use it at 200 megahertz. This is all right. Even though the IC, if you buy it standalone, it's only spec'd to 160 megahertz. So 250 is a stretch. I don't think this will work. But we would need to set up a PLL clock to be able to get that, and we already use our PLL clocks for different stuff. But one interesting fact is, currently we have our, there's like clock for the TFT, and that is clocked 200 megahertz. And this is NTSC, and if I set it down to 166, it would be PAL. So maybe we can use that only at 50 frames per second, the screen, and get the clock for the PSRAM from that. Or we need to like trick around somehow. Delicious soup. Okay, the problem with the interface is, however, now I'm only talking. You can also tell me about your day. Yeah, but this is like an RGB interface, so. The interface isn't like straightforward. There is an open implementation by someone, but doesn't use burst mode, and the burst mode is the best to have a lot memory transferred sequentially. Yeah. So basically, we have like two clocks. One is the memory clock, and the logic clock has to be like at least twice, like half the clock of the memory clock. So dividing a clock is not that hard, so we can do that. Hey Ray. We can do that. But then you have like to command enable. You have to set a command which will be read is 0, write is 1, and the address at this time. I think we can ignore like this command and address. We basically can set this all the time and only do command enable for one clock. And then it's like you have different clock counts for different burst lengths. So if you have like 16 words, then you will get four, like this is burst 16, is it? Yes. Here. So since we have like a 64-bit interface on that, and we only using, I think, the lower 32 bits. This is getting hard now. So you write and then you put like the sequence of words on the interface, like on the bus. Hey Max. And this is like the burst. And write is like starts at the same clock and ends somewhere here. So this is easy. Writing should be easy. Longer burst is like, yeah, this is 32. And you can also mask individual bytes or something if you don't write them, which we will ignore because we just overwrite all the pixels. For now, at least. We can improve it later. There are so many variables that it was, for me, it was quite hard to even like start because it never worked. You don't know what you did wrong, because for the first time to see a working result, you need to do the write correctly, with the right timings, with the right bit set and whatever. The mask is, for example, the mask is like inverted, and so you set it to 0 if you want all bytes to be written, or 1 if you want to mask out a byte, something like that. So stuff like that prevents you from like successfully writing already to the memory. And then you try to read from the memory as well, and you don't know which variable is wrong if it doesn't work. And this is the read sequence. And the read sequence is even harder, because then, depending on the length, it takes a certain amount of cycles, and you have like a delay. A delay before it even, like, it fetches the data somewhere here, or it starts to fetch and then outputs the burst on the bus, data bus, and you only see like the data is valid, and then you have to count, okay, this is the first one, this is the second data, and so on. So this is like a longer burst of 32 words, and so on. So getting that right is really hard. And there is like, from Goin, there is only like a evaluation for another device, not exactly that one. But I found a code, or at least as someone pointed me to someone that did work on. Let me check that. Is this the one? No. PSRAM test. Yeah, okay. That I copied that. So yes, it is, and it's hard. Maybe Max, you can help me, because it's like the interface. I don't know. If you coded like direct PSRAM directly, we could do that. There is an open source implementation, but this is basically like an encoded, crypted block here. And this is the interface. And someone wrote an example. This is basically based on the code. I can give you the name. I have to look for that. So if you want to know, I can share. But this was a working example for 1 byte with the IP core of Gowin, and I extended it by writing like a sequence or a counter. So we see, and I checked also for different words within that bus, which is like 64-bit long. So now I'm stuck. So my test looks like way more complicated, overcomplicated here. So I tried, this is like a dual interface, because we have 2 PSRAM chips which we can address at the same time, like different addresses. So, and this is like the interface, the regular one, and I try to work around here. Wait, did I? Yeah, I removed that. We can basically recode that. But at the end, yeah, it is. Yeah, we can start from this. So what I wanted to do is, this is like the PSRAM display, and this would be like the PSRAM interface, like channel interface from if I use the IP block directly, but I want a simpler, basically PSRAM. It's like a single interface, not the dual memory thing. which I will implement later. And I want a simple interface. So we have to like give the clock and the PLL log, which is basically part of the clock, a reset signal which we only like keep at 0. And then we set it like we want to write every single clock possible, and we want like the command is like write and read, and this is the address. And this here, this is the the hardware PSRAM ports that we have like to drag through all our modules, because it's here. If you remove like that, if you don't pass it through to your through your modules here like that, or if you even change the name, if you change the name, it doesn't work anymore. If you don't move, don't keep it there, the optimizer will throw away all the stuff and your PSRAM won't compile. So you have to, from this IP core, this interface, you have to pass this to the up to the top module. So where's my top module? Top is here. At the end, I have this ugly PSRAM interface. And the strange thing is, what I was confused about, like for a day or something, is that basically there is no definition of the PSRAM interface in the physical constraint file. So it's a little bit strange, and you have to know, so important, you have to know that you need to pass through these ports, which are the physical connections to the PSRAM on the die, or not on the die, in the IC next to the die of the FPGA. So that's the embedded PSRAM. And now the idea is to use the PSRAM to store the pixels. So any questions so far? No. You can always rewatch. Maybe I just throw this away. Nope. So now the question is, we have our frame. We want to store a certain amount of bits per pixel, and we have 800 pixels. We have 480 rows, and now when we rendering like to HDMI would be even higher. So HDMI would be 1280, since this is the only 62.9 that we are able to support. Not currently. Yeah, the scope will be like the next wagon loads. It's a long story. We're working currently on the sonar scanner. It's, yeah, basically, but the external chip is within the IC. So there is nothing on the PCB or anything that you need to connect. Which is a bummer, because having like the SDRAM on the chip would be better. There are probably chips that have that, but apparently that one doesn't. So if we take a look, there's like the letters like NR is like N is like a NAND flash, and R is RAM, and then S could be the SRAM. I'm not sure. Let me click that. Yeah, it could be. No, SRAM. Wait. What is it? Yeah, hardwired. Let me check. I'm not sure what S stands for, but I know like N is the, and S. Oh wait, F. Oh, F is like Where is it? Processor DRAM bytes. I don't know. I was like, so there are different versions of the chips, and this is the bigger one that I also got. No, wait, yes. So the bigger one doesn't have anything on board, but we have like an SDRAM chip on that. I can show that. So the bigger board that we could also use, but now we don't have a board that has like this SDRAM, and you need to use the SDRAM interface. So this chip doesn't have any like RAM on that. So that's that. And what you can see right now is basically the short flashing is every 256 frames. I try to write a frame into the PSRAM, and the other frames it's reading from the PSRAM. So I'm just alternating here by writing and reading, and basically we see only black, so it's not working currently. So back to our implementation. Oh, by the way, we could try to render something. We have beam. Wait, I can show a screen. Wave display. Let's see if that even still working. Might be able to use that. What's that? Oh yeah. Oh, yeah. Yeah, a lot of warnings. Which I can't solve, unfortunately, because I'm not good enough at this. Okay, writing. And that should... Oh yeah. Okay, let me turn on. The mic should be careful with the noises. So I turn on. Okay, here we go. I try not to point at the microphone, but basically, yeah, that's quite loud. Basically, if I put something in front, you can already see there is some reflection. So this is like, I didn't want to mess with that code. So here we go. I just made like a different display. This is like the discrete cosine transform of that. We can try that as well. Which is already using like I think, yeah, that's the sine tab, cos tab, but I think DCT is quite easy here. Yeah, that's really easy. It adds up even like it maintains a floating sum, like a moving sum, so a moving window, and that's what it will display as well. So each sample is only slightly different from the sample before because it's a moving window, but you can okay. So you can see like you can see an intensity increasing, so that, but this is like we are already out of range, oh, you can see. So that's like, we are in the range, that's like in the center, it's like only 3 centimeters is like already the center of the display. So we're only showing here 800 samples, which is not a lot. Still, yes, that's the DCT display, which is already cool. And yeah, now I want to do the beamforming, and the beamforming needs, at least I think it would be the best to have a frame buffer for that. So here we go. Oops. Now we need to practice writing to the oh yeah, we need to do some calculations as well. So what we can do is we can make like a double buffer, since we have like a dual interface, or we can try to start. We can basically swap them because we have two PSRAMs. We can swap basically the one that's written to and the other one that's read while it's rendered. So it sends the bytes to the screen while this one is written, and then you can basically swap the indices and use a different way around. So now we have a pixel clock of 33 megahertz. So we have 33 pixels in this resolution, 33 million pixels per second here. And our clock, so we need like to write the data in bursts like that. We need to buffer it somehow. Like, let's say we buffer a row or we buffer a segment or something. And whenever we move to the next segment, in the background, it will be written to the PSRAM, like block by block. And then we need to calculate how fast we can go, because we have a different, so we have 13 between like the bursts. We have logic can be, so 160 is the maximum of the PSRAM. We divide it by 2, which is like 80. So we have like 80 clocks, and we need to be faster than this 33, which we need, like, if the interface is 16 words burst, we need 14 cycles, I think. It's 14 cycles to, oh, that's to write, yeah. Writing and reading is slower than that. So retrieving the data is slower than burst length, read data. This is, I think, it's like, it could be 14. I don't know what's the burst. Let me check the other example. I think the guy calculated that already. So read takes 22 cycles. So 22 logic cycles takes our read. So this is the maximum. 32 cycles. So we need the slowest one, which will be 30. Wait, 32? No. What was the? 22. Okay, 22 cycles for that was basically for the write of 16 bytes. I think it's 16. Or it's 32. The bus width is, I think it's 8. Let me check that. So, yeah, it's 8. It's 8. Okay, so we have 16 bytes takes 22 cycles. That's 16 bytes. Wait, 22. What? 4 megabyte seconds. Okay, let's calc that. Let's calc that. That's like 16 divided by 22 times 80. That's 58 megabyte per second. Wait, yeah. Divided by 33. So we have only like 1.7 bytes per pixel. So we need to increase the length, the burst length, which will be like 32 or something. So we can get 2 bytes per pixel written, which is already bad since we can't get this clock speeds. We don't have enough RPLL clocks, or we clock down the screen to 50 frames per second, which would work with, I think that should work with the display, and we get the clock for our device here. So if we can clock it at the same time, yeah, that would be enough for 2 bytes, since we need 16-bit, or we can but also just write 1 byte, which is also all right. Both data sets in parallel. So I'm writing one frame buffer and reading the other one at the same time, and that's basically the dual interface. This is so hard already. I'm so sorry. So we have 2 channels, and basically we have 2, if you zoom in, we have basically two channels are 31 bits. Yes. We have to test this. I'm not sure if, like, in the single one, if yes. And we have like 2 frames. And then we have like basically different interfaces, and everything else is the same. So the PSRAM interface with 2 channels uses like the 2 external at the same time. I think it shares the bus. I don't know how it handles that, but we can use like 2 channel mode, or 1 channel, which is then 64 bits instead of 2 times 32. So this is like the end goal, but my goal for today is, so we have now, oh, we did so much stuff here. I need to change the list. Change the list. So this was like an update. Or do we remove everything? Yeah, let's start all over. So yeah, something like that. Then pink has to go. Oh, yeah, trigger snapshot. That's like the other stuff. Scope HDMI, yeah. Are you what do you mean in an array? What do you mean? What's stored in an array? So write pixels to PSRAM. This is my only goal. This is basically the same goal. Try longer burst. Try longer burst. Oh no, we don't do that. Like this is. Yeah, the problem is with that like this would be if we just use one array. We don't do that because we can only do one thing at a time. We can only read or write at the same time. But reading the screen happens by the module like concurrently. It's happening all the time because this doesn't have a buffer, the screen. And also HDMI doesn't have a buffer. We need to write the pixels at the exact moment that they are needed. And basically that's why we need like one PSRAM part. Thankfully there are like two, this dual interface. One interface for reading and the other one for writing. And we basically just switch the roles every frame that we want to render. So it's always rendering one frame and then we switch and it's rendering the other frame while we are writing at a slower speed or whatever in the other one. So this is like try longer burst and then figure out okay, let's figure out the timings. Let's do it first and then longer burst. And then what we do next is dual interface and render and okay, implement double buffer. That will be the absolute goal for today, is implement a double buffer that handles all the trash in the background with the PSRAM, and we basically give it like a row of pixels and it does the job or something, or a block and it does the job. No, there is no screen RAM. That screen has no memory whatsoever. The SPI screen would have that, but this only has like RGB interface, and it expects the pixels at the right time. It's just a huge like multiplexer, demultiplexer. No, yeah, multiplex. Yeah, or something. There's like no logic on that thing. Okay, these are our goals for today. Maybe let's do it. Okay, let's do a new line so it's not that bulky. Okay. So that's the interface. Okay. We save it. So the beamforming refers, I was talking about that before. So we have a phased array here, and we have recordings of like sampling there is like a pulse which is reflected by the environment and sampled by this array, which we sample at 1.28 megasamples, and from that we will use like a lookup table like that one to overlay all the readings for a certain pixel from all the array elements, and basically render if there is something detected. So that will be the beamforming, but that's like a super stretch goal. I don't have even it on the list right now, so that's it. But now all the talking made me hungry, and we can make the fondue. I had the soup, now we have the fondue. It's not molten at all. I will add, we have some pickles. Here, pickles. Sauergurken. Some nice bread with a good crust. So the sourdough bread with good crust. The best. And some cheese, which will melt right now. I made a score on the fondues. 250 per pack. Yeah. 250. I paid 250 for a pack of fondue, and I bought, I think, four of those. Pineapple ham pizza. Nice. Okay. So let me upload your own. Okay. Yeah. Let me check the screen again. Here we go. So every 250 frames, we have the writing, like showing only this is the frame where it's written. So when it blinks, and otherwise we get only black from Or what are you expecting? Okay, so this is our PSRAM single interface. And I have to get it working now. We have a working example, more or less, with written just to address 0, 1 byte. Okay. So I will try to reuse the clock that we have, the 200 megahertz clock, which is basically for the LCD. We need this 200 megahertz clock. Oh wait, yeah, that's for now. This clock is too fast. We can't do that. But oh wait, I have a 100 megahertz clock as well. So let's do the 100 megahertz clock then. I just make this generates a clock that's like half, because we only switch it on the positive edge, which means this will be 100 megahertz. Okay, so I can use that clock. That won't be too fast for the interface. So we can basically tune it later. Yes, I could do that. Or I can basically display the data and I know what's happening there. So I just want to, this is like the simplest way. Oh, this will sting. I just want to do it like the simplest way. I just write. Wow. Stinky cheese. You can see here, this is like the pixel, and whenever the frame, which is like an 8-bit counter, which counts the frames here, and we have a pixel, which is data. For now, it's only like 8 bits, but whenever the counter overflows to 0, it's just showing the Y coordinate. That's why you see like this black to white horizontally, and otherwise we just, oh, this is the shift. What is the shift? Shift is 0, okay. Yeah, we can just do it. Do we need the shift? No, that was like, okay, yeah, otherwise we just do that. Data in, yeah, have this. We don't need old code. Yeah, so every other frame we just reading from what we get there. So now we can, this is like data in 64-bit. Yeah, that's mine is also real Swiss. And I just take the Y coordinate and repeat it 8 times. So the interface is 64 bits, but usually it's 32. And since the single interface is doing it in parallel, we actually write per clock. We write not only 8 but 16 bits at the same time. So that's why we have 64. So there are like 4 write operations or 4 clocks. And wait, 32 bits each. Am I right? Is this actually working? I don't know. We have to figure it out, okay? However, this is the address. We calculate the address, and yeah, this is our interface. We just want to do that. Swiss milk polymer. So the idea is now to have a simple interface and basically get the data out, but we don't actually know how the data returns or when or whatever, if it returns or when. So that might be hard to do. I'm not sure, but let's go inside the interface here. Okay, we have a clock. So the PSRAM is clocked at, yeah, this is the PSRAM, this is CLK, and this will be counter 0 since the logic clock is half as wide as, let me stir for a sec. I think it's time for the extra juice. Yeah, that's good. Let's let it work a little bit. So I don't know a lot. So I have two different ones. So the Tang Primer 20K doesn't have inside the chip any like only block RAM, not actual, but it has like external DRAM. So this is like DDR or whatever. What is this? I don't know. So that's like it has like DRAM interface. That's that one, but I'm using that one, and the PSRAM, there is like a die next to the FPGA on the same IC. There are even like two WinBond PSRAMs inside that chip. So it has PSRAM, but so there is on this here we have, this is like the serial. This is I don't know what is that. That is flash. Oh, what was that thing? I'm not sure yet. No, I don't know which one it is. What is that? A small thing. I can check, but there is not much on that board. Most of that is embedded. And there is, yeah, that shows. HDMI, DC. Oh yeah, we have, this is the DC to DC stuff. Let me show that. Yeah, because we need like different voltages for the FPGA. That's like the small one is DC to DC. Then we have the JTAG, FPGA. There is the flash, SPI. Yeah, SPI, that's just only a connector. There is nothing there. There's not an IC or anything. So there are only like actual active ICs are only like 3, which one of those is, yeah, and the power regulator. I'm hungry now that I tasted the cheese. Okay, here we go. By the way, I'm keeping now the links to the boards, like affiliate links in the video description if you need them. It's AliExpress and it's cheap, and I bought it from the sources as well. Nasi goreng, that's like sophisticated. That's way too difficult for me, because fondue, I just buy this packet which is ready, finished. Okay, I think the cheese is ready. A short pause, screen capture. So now that I talked so much what I was doing all the week, what have you been up to? The viewers that are rewatching the stream can skip probably 5 minutes while I'm eating. I promise I eat fast. I'm taking folic acid now because you guys scared me so much. My diet is great. I eat a lot of cheese. Random number arrays. What did you do with random number arrays? Hey, Bachler! No, actually, I'm the one. I'm the one that that suggests eating more like veggies or salad. She would usually eat like only maybe potatoes, but she would never eat like salad or anything. So I have to enforce that in our household. She is eating today. She's eating soup. The one that I had before, she cooked that. I just grabbed some soup before. Yeah, cheese. Fondue. Yeah, but it's like just like a simple one, bagged soup. I think. Not self-made. But she also does a good self-made soup. This is my veggie now. No. Yeah. Whole grain. Why would someone eat whole grain? That's like extra waste. Isn't whole grain always like extra waste that you can't digest? Please explain why whole grain is so great. My diet is bad. That's probably why I wake up with random pain and back pain or something in the night. Now some energy booster mini juice, but sugar free. Okay. But I like couscous. Couscous salad is nice. Like tabbouleh. I love tabbouleh. A friend of mine is a French guy, and he makes the best tabbouleh. Whenever he makes like complete bowl, because whenever I visit him, because he knows how I love it, and I will eat it all the time. Okay, but back to the coding. Here we go. Screen capture. Okay, so we have a clock, and no, never tried. Even like peanut butter is not usual here, but I eat it like from time to time. Okay. So let's start all over. Okay, here. Recipe. Okay. So, this is our PSRAM interface. This is like the simplified version here. Nah, it's all right. Wait, don't I have like... Wait, chat phone. Ah, here we go. This is the good one. Good one with some extra stuff. So, I have some scenery here. Maybe I put this, whoop. What is that? What did I move here? It's another one. Okay. That's a better organization. Okay. So, data in, data out. The width is 64-bit. But I don't know how well that works. And I maintain a counter, and basically half the speed of the clock is basically counter 0. But we can I mean the It will be simplified if we or do we like use an external clock for that? We'll solve many world. Okay, so CLK half, and then basically which is basically the same. Inverting on that. And what I do now is, the interesting part is that from outside I don't even have that clock, which is not that great. I might want to pass on the outside clock and good question. Okay, let's do it like that. We use that clock and input PSRAM, which is basically the other one. So, and we don't need that for now. This will be CLK, and this will be PSRAM CLK, okay? And Verilog, data valid, yeah. Staged, and we have init done, which is basically if init done, begin and end. Basically, the interface, I don't know if we even need to count. The interface only like it initializes for like 6-7 clocks or something. PRAM, I don't know. And let's do the following. Can we PSRAM IP core generator? Need to remove a few tabs. PRAM stalker. PSRAM display. Okay, let's take a look at the clocks. Can we get like pixel clock, input clock, 33 Mac? How do we get a clock that's twice as fast? We need to count to 3. So this is 100 megahertz, but we can also, since this is the pixel clock, this is hard. Oh yeah, block RAM. Yeah, that's like on FPGAs. That's a small RAM block that is basically more efficient to use than D flip-flops. Usually you have only like in the thousands of flip-flops, and then block RAM is like hundreds of thousands, so much more dense. Okay, how do we clock it? I mean, we can use like the logic clock. Or let's do PSRAM, do the naming convention like that. CLK. Okay, let's do it like that. And we will synchronize always. Let's clone that. Okay, and we will sync basically these are like signals, and we will synchronize the stuff with this clock inside. And we basically tell our interface, this is our logic, it's clocked like that, but we will stage everything inside with D flip-flops, so it will be synced to this clock, and this is like the clock of the PSRAM. And PLL log, I don't know, probably still work because this is based on the same PLL. The compiler or the planner, this is not what I want. Yeah, it complains about it can calculate that, but the relations, but I don't care. Probably could be a source of error at some point. We don't want to reset, and we just enable it, the comment all the time. We can comment enable so we know what's meant by that. Data in, data out, and the address. That's all we know, and now I will change that. CLK PSRAM, and then CMD and enable, command enable. Here we go, and we have data in stage, data out buffer, data valid, and basically address, and command stage and command enable stage. These are all wires, and we will here, this will be all enable stage, because we want to have this happening. Data valid, address stage, clock out is not important to us. Address stage. Do we even want that? Yeah, we can. I implemented all this stuff. I just need to check if this will work like that. Always on clock. Do we even, what is this? Sync. Okay, let's remove that. And so what we do is let's have this 8-bit, the sync, or clock okay, this is the clock count, and this will be 0, but it doesn't matter. And then we will just do it again. So if init is done, otherwise we ignore everything. I don't know if this is already done in the interface and we need to do it like that. I think, and yeah, we can do both interfaces, but I think it's only used one. Okay, begin. And so now, not sync, we have the clock count, so we know what's meant by that. Every time we increment the clock count by 1, and then yeah, if clock count is basically 0, this is where we try to synchronize with the longest possible, like the required clocks for reading and writing. Archer was cool. We basically write, since we synchronize with the outer interface, we do it like that. We count the clocks, and then whenever we start like a new cycle of reading or writing or whatever, we stage basically the comment, the data in, and we always stage data in, even though we might not do anything with that because we just fewer branches here. It doesn't matter. At the end, it will generate like the same logic. Address stage. Basically, we copy the address right at this moment. Then we do the following. So might be interesting. I think we don't even need to do that. I just do it right now. But we also do comment stage, and then we comment enable just to synchronize everything, huh? Oh, stage was missing, so we enable it. With 1B1, because it's the first. No. Okay, so we take basically the comment enable. We can also disable it from outside. Okay, so it does that at the first and data in stage, valid address stage, Thankfully I checked that. And this is the buffer data out. And what we do now is we write only this one and ignore all the other counts. So if now we can do, so command is read write, and now we check if command stage, this is else, so we are not, this is not the first cycle. And if command stage equals 0, this is right, oh wait, right. And else, or yeah, right, else begin, this will be read, okay, and so write and read. Clock count is always done here. Yeah, this is, we don't need that. Okay, so we take a look at the code and the timings here. Okay, so we are in this scenario, which will be for writing, like we saw in the other example, PSRAM test. It's basically write takes 14 cycles and read takes, wait, write is 0. Oh, wait. Oh, I can turn off the, geez, I think I'm done for today. Read. Aha. State begin. Oh yeah, the example is basically Verilog, where is it? Command is 1, which is write. Yeah, so he does that. Data mask is 0. So I need to do that as well. Do I have the data mask? Data mask is 0. That's basically write all the bytes, okay? And then, since we have already the data there, like the first words there, and we ignore the rest of the burst, we only need to end this. Oh yeah, we also need to comment enable stage is basically 0. So we only enable it for 1 clock cycle here. The command address, this is ignored, and comment enable is basically, this is set like that, okay? And now we have We can clone it from the example the dude figured it out. So if cycle, yeah, we can do that. So common state, so it's right. Then if cycle, which is, oh, we can also clock count. Cycle is also a nicer name. Let's rename that. At the end, I clone a complete code. Cycle, common stage, cycle. Let's do it here. Oh, yeah, we need to do an else here. Cycle. Zero. Interesting. This overrides that. Okay. Okay, so if cycle, I like that. Okay, cycle. So basically, here we are done with the write operation. Done writing, which is basically cycle 0. This is Verilog. This is Verilog, system Verilog even, because I like some features. And this is state, which is basically of this flow here, which we don't need. So this is right. Now we need the read operation. And the read operation is a little bit more tricky, because we need to do the following. If, oh, we need to count rec word count, and yeah, we can, we don't need like that many. Let's do 3 word count. Okay. Here, word count is basically a reset. So we want now the read. I show you the read cycle, which will be, we did this now, and we only like write that and count the cycles that we need to consider that it's still writing the words that we actually don't give it. So we could store more than that, but we ignore it. And then we just end the write thing and start all over again. And for the reading, we need to wait for all the words to arrive, which are 4 words, and we need to read data valid. So we check, this is not the right code. Here, we need to if to check every cycle, how did we call it, data valid, and we only, yeah, this is what we used before as well. Data valid 0 if begin, then if valid wait a second, if we stored, oops, so we start with 0. It's still 0 here. We increase by 1. So at the third iteration, we, like of the last iteration, oh wait, not data valid, sorry, word count. So word count, this is like the last word that we currently receiving. So we have received 3 words before, even though, so for you not to be more confusing, word count. So the funny thing about Verilog is this assignment happens at the next, like for the next clock cycle. So, oh wait, we can do 1 bit actually. So it will be only increased after that. So that means that this, we received 3 words before, but we could also write it like that. It will still work like that. So all of that happens at the same time. It's a non-blocking, was the name of that assignment. Okay, and here we are done. Are we done with reading then? We should data out. We should be read done. Data out, output, and no, it turned it off. Okay, so data ready. That will be the signal, which is a register, and we will set it here. Data ready to 0. And we will, or you know what? We can call it busy, or no, we call it ready. So we can use a positive clock. Ready. Whenever we are ready, no, done. Ready, done, busy. No, ready is okay. So when we are ready, or how do we call it? When we received all the data and we also sent all the data. I think I will just call it done after this. Okay, here we go. done is that. Yeah, let's do, for one cycle, we do done here. It will basically blip for one cycle every time we are done with something. Like done writing and done reading. So we always know when we are done with reading, and now we also chief word termination. Data out. So now we just output I don't know if we need a register. Yeah, we need a register here. And this is basically data out. Yeah. Oh yeah, acknowledge is also a nice one. Data out stage, but we need on the first word, when we receive the first word, so data valid, if word count, did we reset word count? Yes. If word count is 0, then we do the following, data out stage, data out buffer. So we only, from the burst, we only take the first, and we can kill that. All, it's basically the same code. Okay. Oh, yeah. What does mean rec received? Data received? Yeah. Ring a bell. Okay, let's hope it does anything. I have no clue what we are doing. Does the PSRAM display do anything? Comment, data in, data out. Oh yeah. And here done. And then basically, yeah, we ignore the done. We ignore the done for now. No compilation errors. What? No compilation errors? What? Kidding me? Okay, interesting. Yeah, apparently we are good at stealing code now, at coding. Yeah, at Verilog. Something's nah. Look like the glitch in the Matrix. Okay. Okay, now we need to do the following. We need, this is the wrong one. I just put this away. Yeah. But I'm wondering why we always get this block here. I saw similar result. Nah, the TFT driver. I had this before, like this result. And you can see like the intermediate, the reset frame. when we try to write, is also there. So let me write, no, it tries to write all the data in. Okay, let me check the code. We have something, but you can never know what is showing there. It might be like, I don't know what it is. Now we need to like synchronize with the outer stuff. So we have the pixel clock here. How about we make the pixel a register. And basically what I will do, data in, data out. This will be also, wait, let me take that. So the interface between the clock command, yeah, whatever, wire address command. Yeah, I don't need data mask here. Yes. Comment wire, wait, done. Rec, and rec. Wait, no, data out could be a wire. Is it even used? Yeah, should be. And I will comment enable. Oh! No, wait, we're not even using that anymore. No, we always send a 1. I will remove that. Okay, comment is basically here. That's like messing around with clocks and whatnot. Really? Always add pause edge, and then we do done. Whenever it's done doing something, wait, read. Yeah. Valid. What is valid again? Oh yeah, that's all about out data. What is out data again? What is this? What is this? This is like old trash. This is also old trash. Okay, valid is the pixel stuff. This is the clock. It's the clock. It's the frame. Okay, this is the screen stuff. This is the registers that we are doing here. And whenever we have a done, oh yeah, comment will be 0, which means it reads. Do we sync it like that? We want to sync it with the pixel clock, not with... Whenever we write, we sync the write with... What is the right clock here? Reading could be done... Okay, let's try that first. I hope it starts on its own, because we have it enabled, so it should do something. And then if frame is that, begin, we... Wasn't it a like original Star Trek series now? Okay, when we are at frame 0, we set command that, and data in that. Data in is basically what else do we need? Data in, data out, address. Oh yeah. Address is wait, this is synchronized inside. It looks like I'm synchronizing twice. Okay, I do the following. When it's done, I just read data out . Is it data out there? No, it is already a I think this is all unnecessary. We need to find the bug somewhere else. Data in, since this is all, there is like, data in is just an input. Yeah, we need to take care of data in. But that's done inside. Data out is also taken care inside. Now I don't see the issue, except maybe we need to set the pixel at some point. Comments. Wire. Okay, let's leave it like that. What do we do with the done? With the done, we just set the pixel. That's the only, always at done, we just set the pixel. If okay, basically this is it. I try that. Now it won't compile anymore. Implicitly, yeah, no, that's not doing that. Oh yeah, wire. No, rec. Huh? Oh yeah, I need to define it before that. Here. Let's try again. Oh, I don't need that. The mask would be even bad. Okay, clock, LED, clocks, okay. That shouldn't change anything. The only thing that we have now is that we don't... Yeah, that didn't change anything. We should only read what is happening. That looks like still a synchronization issue. So let's try. Hey, Dutch Maker. Let's try The problem is the reading, because we write like only, and the data is changing, we write like only every few frames, but the data is changing here. Let's do the following. Clock pixel, and we set only the read every few pixels. Oops. Or we do it only when we really need it. So we said, yeah, Nah, yeah, nah, because it's not doing like this single stage here. When it starts a new cycle, it basically clones all the addresses or whatever oh, sorry, you can see. So inside we have like a clock and we count the cycles, and whenever we start something, oh, I see something here, command enable. Yeah, if init done and no, wait, if cycle and command enable. Yeah, we should only do that. So we should not cycle. Also, we should not cycle here. Cycle. So we do it like that. Cycle will be 1B1. No, we need if command enable. This will be our deal. And this will be inside that. So we will wait for the next, not just repeat every single thing. We'll only wait and not count anything. Yeah, just at another end here. That's a lot. Nested. Nesty. It's nesty. Okay, so it will only start working and then cycle is 0. I hope that works, otherwise it will not work. Okay. Did I change command to be? No. Wait, where's command? Wire. Where's command? Oh yeah, wire is still wire here. Okay, we'll just move it over. I have this. Okay, let me try that. We changed a little. Let's see, let's not change a lot at the same time. It's a little different. It's changed. Now, next thing is, let's handshake this pixel over. Let's synchronize. So this will be register, and it will be, oh wait, no. Done. Command enable will be 0 in the beginning. Okay. And every okay, what? 7, 0, and let's OR it. 0. When we do that, let's try to comment enable done is wait. Oh, I see a potential thing. Done. Let's do done. Oh, it is a register. And it's only set to 0 and it's set to 1 when it's done, which is nice because then we can always check comment enable. Okay, so not yet. That's later. If done, comment enable. Oh wait. Oh wait. We need a busy signal, not a done signal. Shoot. This is the problem is with that. Does it work like that? Oh no, we can set busy. Oh wait, no. We can set done in it else. Oh. We can set it ready. When do we set it to done? Initially, there must be some. Is there? Yeah, is there the sound? There is like initial block, but initial is only for simulation. Yes, it is actually. But how do I set, when do I set, yeah. It will be always busy though. I need like an initial state. Oh wait, cycle is 0. Comment enable. I have an idea. And else done. It's the same. Okay, so yeah, this is stuff. Okay, so this is else, and it will be also else. Here, this is initializing still. We can do the busy state. I need to invert it at some point. Okay, this is initializing. And if done, comment enable. And then if done, pixel and comment enable. Oh, wait. That's concurrent. How do I do it? Only in that case. Else. Yeah. So basically it will disable the command in the next pixel cycle. I have no clue. I might skip. Yeah, but we need to set it somehow. Now it's confused. Which else do you mean? Yeah, syntax error. What is this? Oh yeah, I don't need that. I don't know if this relation. I don't know how to set this. Done is an new clocks. On what phase? Yeah. What is it doing? What is that? Wait, this is right. Wait. This is confusing. This shouldn't be. Okay, every 16th pixel, comment enable. Oh wait, do I even use that so far? No. Okay. I didn't use it. Now every 16th pixel should be. Nope. Wait. Oh, interesting. This still works. But we didn't write correctly so far. Uh-oh. I'm showing some stuff, okay. On done. Pixel. I think this is irrelevant. This can be here. When it's done, we can disable the command or following. If it's done like that and else yeah, let's do it like that for whatever. So every, oops, errors. Wait, what's going on? What's missing here? Begin, end. This is a boring stream, isn't it? Okay, we need to write the frame first. I think we don't write anything. So basically, if frame equals 0, this is like when we write and else do the other stuff. Because I think we're not even writing right now. Oh, that needs to be here. Wait, we can do it here. Done. Yeah, no. F this. It seems it might not be ever done. Oops. If end. Begin. US static. Yeah. We are glued to an event horizon. Like sticking flat. Big, so No, this is not good. No, we will miss. This is not good. This is not a great way to synchronize. I think we need like an asynchronous interface. Is there a pattern for that? So what was... Here we go again. With this stuff. Okay, we are writing, but we are not reading correctly. And I don't know what's happening here. Can we do like one address only? Yes. Let's try not changing. Let's try keeping the address fixed. Else, let's keep it 21 bits. Let's say 100. Let's keep, while we're reading, let's keep the address fixed and see what happens. Because the flickering looks like it's reading from the wrong address. Oh! Wait, that's not what we should see there. What is that? It should be still 0. The panel is all right. We can write to the panel easily. We done this before, so the panel is all right. We have a nice interface for that. I'm seeing here a problem maybe. Wait. The address let me change the address to register and assign. It will be delayed, but however, I don't care. Address is basically that. Because like multiplication might not be correct at all times. So if we clock it, we have the result here. It should be right though, I don't know. I'm trying to grab any straw here. Frame is 0, okay. Let's try again with that. So the address doesn't change all the time. Okay, old behavior. Let me try. Okay, we are doing... Oh, we can throw this away. And then we put in launcher 1 rocket. I'm getting tired already. Oh no. Should we write something fixed, like data in, like a fixed value? How about we write a fixed value there? Because I had a similar issue before where it was showing the address at the pixels or something. It's really strange. Okay, a value of 100 or something. 100, and this will be decimal 8 bits, and this will be repeated 8 times. So every bit should be like a gray value. Aha! This is completely messed up. It lost 400,000 feet. When was that? I might have seen it, I'm not sure. Okay, I don't know what we are seeing here. Oh, okay. Then I didn't watch it. No, unfortunately not yet. This will be the goal. Let's try writing. Okay, what we are seeing here, my friends, is not what I stored. Let me remove it, plug it back in. Let me rewrite it. I deleted the PSRAM contents, okay? Because it might be like the PSRAM is still holding stuff. Okay, what we are seeing here is not data that we stored there. Because I don't store anything. Why it's frame... comment, okay. So let's remove that. At what stage does it break here? So data out is trash. But it's always command enable. Yeah. Yeah, the working code. Look, there is a bitmap every 256 frames. You see that gradient? That's our test pattern. So I can do it like for a few frames. Frame. Let's do it. Oh, let's frame is smaller than like 10 or 60. Okay, so we will leave it. Yeah, that's a test pattern. Now here is it for 1 second. So test pattern. This is actually what we get out. Okay, do you see? This is my test pattern. Okay. So we should see output similar like that, but no. But the output is changing all the time, so that isn't possible. It's like I'm wondering if it has something to do with the clocks. It can't calculate the relationship. I have no clue if this might be an issue. Ah, this is mean. Why do I get? Yeah, it is. Yeah, this is what we do. This is what we do. Every, like, of the 256 frames, 60 frames, which is 1 second. Oh, you can see the code. Here is the code. Here. And this is where we output basically Y on the screen. The Y coordinate. Other than that, where's my... Yeah, now you can see. I need some booster. Ah, nice. Ah. B12? What is B12? Vitamins? So, what we get trash from data out. Data out gives us trash. Why? Und det feurig. Oh, really? No. Are you sure? Maybe almonds, chocolate almonds will have some vitamin. Does it say? No, doesn't say. Do almonds have vitamins? Let's ask ChatGPT. I don't Google anymore. I use only ChatGPT, even though it might lie to me. No, not B12, apparently. Oh, meat, fish, eggs. I had eggs today. Milk, cheese. I win. Wait. What? Okay. I might have an overdose of vitamin B12. Oh, it's wonderful. Blender elements. What do you... Is it also text? Elements. Yeah, but Blender uses Python. Python, I misspelled Python again. Look at this. Here you go. You're welcome. Nice, it has an execute. The interesting part is when I asked it for Blender, whatever, it just is like this. It doesn't even know that it knows a lot about Blender or how to make stuff for Blender using Python. It just resigns, oh, I don't know. The choco almonds are the best. This is one of my favorite snacks. Okay, a few more. This is like this is like, you know, the example with this blender is like you at the airport, you're meeting a pilot with his whole uniform, and you ask the pilot, can you please explain, or can you fly a plane? And he would say, I can fly a plane. And then you sit him in front, like in the cockpit, and he says, oh, well, let's start and fly. Woohoo! Or, I don't know what the plane is. Ah, you mean this thing? Woohoo! My button is complaining. I need to switch. Here we go. I would
I would jump out of the plane if that happens.
Huh? Why did it disconnect?
Flying is not the problem. The
Uh-oh.
landing is.
Next time you will ask me at the airport, I will
What?
be prepared.
Can you land A737?
Okay, sorry. Huh? Is it? It's confused. It lost connection for a second. And Discord is completely confused. Ah, I don't know what to do. Okay, here we go. Why is this only 65%? Okay, let's fix our issues here. So this doesn't work. Data out. It's confused. Okay. Oh, wait. Oh wait, let's do a new session. The standard answer. Okay, but you can get the information. I basically know what it says there. Yeah. FCOM will provide recommended speeds, different flap settings, landing configurations. Typically, a normal landing should be around. Huh? Safe altitude during landing is 0, not -1. That's like the perfect altitude. Okay, we should ask it that. Train. Okay. Okay, let's ask a joke. Okay, is it a submarine then? No, commercial airliners like is not designed to operate underwater. Oh, I clean aero aircraft's altimeter system. Okay. $100 annual and progressive inspections. Interesting. I mean, you can learn, like, get an impression of all the stuff, but it's interesting. How tech needs the hull be of a submarine diving 100 meters and what's stainless steel type should be used. Ten bar. Oh, come on. Ah. Okay. How thick needs the whole of a perfect sphere of from steel? How thick needs the whole of a perfect sphere from to be to withstand 10 bar? That it can't calculate that. It's confused now. It doesn't understand. Oh. Ah. Oh, really? Oh, yes. Oh, interesting. Okay, okay. The radius is 2 meters. Most probably. Oh, 1 meter. It gives me an example. Inches? Oh, please. What? I mean, I started with meters. Or 3.6 millimeters. Okay, yeah, 3.6 millimeters. It's not that bad, but it's only a 1 meter radius. I mean, I would fit 1 meter radius. Oh, I can't type. I can't type. Is it done? Oh. Is the Oh wait, bar is not psi value. Let's see if it can calculate. 7.3 millimeters thickness. Oh, that's like almost. Okay, not that. Okay, let's make it 10 millimeters. I mean, I can't even put my hands like that. It's like already 2 meters is like the door and, or let me, so, no, my wall is higher than 2 meters here. And it would float, certainly. Of course, it's completely empty. And the volume is wait, we have 2 meters, it's 4 meters in total, which is like 64 cubic meters. Wait, is it? Yes, 4 meters. No, it's, yeah, the sphere would fit in 64 cubic meters. Wait, it's 33 tons. 33 tons, 64. Yeah, it would float, certainly. Oh, is it 4/3? And salt water is even heavier, so be careful if you use it in in your bathtub. Since when does it calculations? Oh, 33. Wait a minute. That's the volume of what? Wait a minute. That's the of a sphere, a solid sphere. It needs to subtract. It needs to subtract the volume. Yeah, that's wrong. There's missing. It needs to subtract the volume of. It's not that heavy. It's like 33,000 tons. So you would subtract the volume of 2, like 1. What's the thickness? 7.3 millimeters. So you calculate the steel. This is the 33,000 tons minus 32,000 tons, whatever the volume is when you subtract 7.3 millimeters. So it would be like 1.992327, and subtract that. Yeah, that's wrong. Blindly trusting ChatGPT. Hollow sphere. Yeah, whatever. Didn't we want to code that here? That's correct. What airspace? What do you mean? Wait, Tech, are you a pilot? Wait, Tang, I didn't get this. Did you? Oh, I'm envious now. I can't do that because of my color blindness. I don't want to be like only a day pilot here. Holosphere. Yeah, I will hollow display here. Oh, we're wasting time. This is unsatisfying. I mean, I did a lot of explanations in the beginning of the stream, but we don't have any results yet. We don't know if we stored anything, and we don't know if we retrieved anything correctly. Okay, so we are getting trash from data out buffer. Word count is 0. Data valid. So cycle is 0. Oh, really? Oh, nice. Okay. I don't know what's happening here. Buffer. Let's try a fixed value here. So let's try to do the fixed value here and see if we have like some odd issues. Yeah, whatever. D100. It can't calculate this stuff. It flickers a bit. It flickers a bit, but there is something. What does off the handle mean? Okay, so the output the screen seems to be what? Why? Okay, so word count. Word count is 0. but there is a valid output. Now, the interesting part is out of order. So the issue is now that the data out buffer valid data out buffer address. It should be valid at this time. So data is valid. So we have a clock. The initialization is done. Command is enable. Okay. Something is going wrong here. Let me try the different interface. We have let me do it here, new file, Verilog file, PSRAM, and I copy this definition, which we worked before. This was working 22 March, from March 22. And yeah, I don't have that money. I don't get it. What does this mean? Okay, whatever. PSRAM memory interface HS. Is this the same? Is everything encoded here? PSRAM top. Is this the same? January. Oh wait, that was generated back then. Okay. Let me try and disable that. Okay. Did break. Warning. I'm wondering if there is an issue with the clocks somehow. That will, I bet this will not solve it. No, wait, we need to... Why is the data out buffer not good? Yeah, that's the same issues. Do you think it could be the clock? Should we try different clocks here? We can use clock picks as the logic clock. And and half the clock here. Okay, now it's not complaining anymore about the clocks, but I bet it won't work. Yeah, it's just black. Why though? This is not satisfying. Oh wait, it's the different way around. We need the faster clock needs to be PSRAM. Okay, let's try again. Now it can't calculate again. It says here. Yeah, it's basically the same, but why did you people let it expire? Okay, now we have no problems with the clocks anymore. It's expensive to keep it up or what? Yeah, here, that's not working. It's black. Because it's like multiples of that. Do I need Okay, let me change some things. Add new file. Okay, let's clone the PLL here. And the clock will be oh, that's expensive, yeah. Oh, do I have now two PLLs? Wait. Single. Okay, I see the problem that I will get with, oh wait, chip. I need to rename that. Okay. Because it's another configuration. Memory clock. PLL log. Sys clock. Clock D. Sys clock it is, okay. Okay, now we have two. Oh. Wait. Oh yeah. I need the signals maybe. Sys clock. Clock. Wait. PLL memory clock D. This is our clock here. Okay. Oh. Yeah. So this is PLL log. I found out why some people, oh, you don't see anything. Found out why, or I have impression why some people like to use the underscores, or some people use camel case like I do, and that's basically has to do how accessible maybe the underscore is. Okay, no, it might be on, how is it on the English keyboard, but it might be just less accessible with the German keyboard layout, or am I wrong? What's the English keyboard layout? So it might be just a convenience factor. Wait a second. Oh, it might be even less accessible. It's next to the backspace. Okay, so I don't understand. I thought it was like, oh. Ah. Web arrived. Why web? What? Allows double click? Not in the chat here. Interesting. It might be dependent on your IDE. Yeah, that depends on the IDE, I suppose. Okay, we have no success here. I need to step back or something. Why is it reading the wrong stuff? What is happening here? Wait, what is? Did you mute you or what? Do we need to step back, my friends? So let's try this again. Error. What? The number of ports. Good night, Tech. What? What is that? Resource limit. Yeah. What is it? What is the issue here? The number of ports. Huh? Which one exceeds? Why does it need so many ports? What is going on here? Huh? Oh, wait. I see. Oh, wait. There is a clock out. What? Oh, wait. Uh, all that stuff happens at clock out. Yes, that might be it. Then having oh, for what? Dave Odessa, good night. I'm hoping to. It shows a pattern. It shows a pattern. What? Dave, don't go! Don't go! Dave! We are there. We arrived. We have. Let's write. Why? Yeah. Okay, it might not work. I have no clue what we are doing here. Ah, okay, you can go. It's it's still the same. Okay. You can rewatch the end if you like, but I will try a few things with the new knowledge that we achieved here. That's somehow clock. Wait, PSRAM, PS clock, PSRAM, PL log. That will be the clock out. Let me try again. Yeah, it looks like PSRAM single. So we are using now the clock that we are getting out of that clock out, init done. So now we have clock done, init done. Begin. I'm wondering if we should do quick pixel clock now here as memory clock, or pixel clock and the other one still like that. Shouldn't complain about any clocks, huh? Yeah. Yeah, that's basically that. It seems like the similar effect. Okay, uploaded but it didn't change anything. Good night. So pixel clock doesn't help. So pixel clock, memory clock, but I changed so many things that I don't even know how do we whatever. Good night, Jordy. Okay, this is, we don't need this, we don't need that. Data in. This is staged internally. Let's try again with, oops, with writing something fixed. Upsala. Nope. Okay, it's still the reading, but we are using the right clock now. So what's the issue? Out buffer. We're using clock out. Init done. Let's do that and let's do that. Since this is irrelevant, we don't need like a step in between. Nope. Debugging is the worst. I'm so sorry, peeps. Wait a second. Do you think I have read and write inverted? That would be funny. We can try something. Data in, no, but it's fixed. It's always fixed. Updating the data line multiple times during each horizontal line draw. No. Mirrored, no. No, 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 no. Comments, but I said that won't work. I mean, I can try. If you think that's the right. That would be funny. But you look at that, right is 1. Yeah, no. Nothing happens there. Yeah. Okay. Okay, let me check. Clock out. I check init done, init calib. That's correct. So command psycho Oh. So command enable, but this is staged. Stage begin. It only starts. Let's write multiple times. I mean, what is then cycle. Okay. What is that again? Is this the hard-coded value? It would be funny if it works now all of a sudden. What? Okay, let's what? It works? It alternates. It's from memory. Okay, let it move. Let me move the pattern. Let me alternate the pattern every frame. So we output a dark frame. So clock edge, okay, 0. And we do it if frame 0 and we write why comment enable? What? Oh, if it's done, huh? Why here? I don't get it. Okay. Data in, let's do frame. Let's try. Should be flickering and moving. So I changed a little few things. No, it's not moving. It's probably pre-written. The PSRAM, we written it somewhere successfully, and now we disabled it. It's not written anymore. Okay, you can see it, but it's happening. It will burn in. Okay, multiply. Wait, what? That didn't change. Wait, what? What is that? This is like a write or read delay here. Okay, it's not writing anymore. No, this is like a delay memory. It seems to be, I don't know what. Okay. Now we need to check if it's shifting by 1 pixel. Oh no, no. Oh wait, is it shifting? No, it's not shifting. What the F? Okay, I try a different pattern. I mean, wait, the pixel, okay, I still write. We need to write, I seem to be, oh, interesting. Okay, this is X times Y. Let's do X and Y. Because multiplication seems so random. Or we shift it by okay, here we go. We are still not fast enough with the reading of the memory, but we are able to read something. Okay. I need RGB. Okay. We're getting somewhere. We need a multiplication. That's wire 31 0 pattern, which will assay part, yeah, equals x 8 times I don't know if the result will be like, or this is like 16 So let's make it 15 and then part 8, 8, okay. Upsala, plus 8. Yeah, that's the read-write delays. Okay, so what we basically see is, I can maybe explain that. Here in this corner is 0. And what we see here is the data that's read like delayed. So we should see a square, oops, a square that ends here with white and should be black here and black there. And this basically overlaps from the other frame. Something like that. What I'm wondering is, why is it here correct? Oh, wait. There is like a blank time, but why is it overlapping here still? Okay, let's change some clocks. But I think we are able to write to PSRAM, read maybe? Who knows? Oh yeah, write might be also like delayed. We are using the pixel clock now. We should be able to use a higher clock for that. Should we try a higher clock and see if we get a better result? Oh wait, we already using the memory clock here. Oh no. Should we try using No, frame is not more. I removed that. The pattern is now a multiplication only. X and Y is multiplied. That's why you should see a square, and I take only like the 16, the upper 8 bits, which should be basically that. What I will try, let me try if I can do that, like a 200 megahertz clock. This would be interesting if I can work with a higher clock. Syntax error, what? Oh, see, okay. Yeah, but I don't think the PSRAM supports that, so if it's a hack if it does. So the streaks should be smaller. It's somewhat. It somewhat works. I wouldn't dismiss it. Okay, okay. Lol, overclock it. Should I only use like read at address whatever and then keep it there? Yeah, that's a plus. But I don't want like to make it introduce possible errors here. So I will keep the bad clock. Let's recompile. Okay, it's interesting now. I would end the stream, but I want to see like an error-free display, at least without the shiftings. So I would try command enable. If done, pixel. How about we don't care about that because okay, this is the new clock again, and now we don't do the done anymore since the it's staged anyways. Okay. This is still okay, in my opinion. Oh, wait. Huh? What did it finish here? There is like an extra end. Did it ignore an end? Okay. Okay, let's try again. Not that I messed up something. Okay, now it changed. Okay. That is still working. We should try to program it with disabled and enabled, and now I will program it again. So we will see. Okay, the pattern is still written. Yeah, it will be white or black. We're reading correctly. It's now just delayed. So let me do one thing now. I will just try to enable like the address should always be only a multiple, like the address this is all right. Writing. No. I will end this right now. You should be curious then what's we will just end what is this 21 hex. Oh wow. What's 21 zeros? Whatever. That's 5, 6. Okay, this. I will try to read only every 16 bytes. So we don't get the flickering, like moving around. No, we still get the flickering moving around. Okay. What's if we do that? It's like 256. Okay. E. Every 128, and I will leave that only enabled when X like or no and like that. Strange. Oh no. Yeah. This is a peak in my everyday life. Trial and error. Okay, it seems I don't change anything at all right now. So command enable doesn't do anything here. Yeah, you know what? I will end the stream. Unfortunately, not enough. I'm not sure if I'm writing the pixels right now. I do something. Something is stored for sure, since we are retrieving the patterns, somehow the patterns that we write to the RAM. Read them, figured out the timings. We fixed one thing. Try longer. Oh, that's all gone. But for now, I found 1,000 ways that it doesn't work. Okay, here, this is PSRAM for you. It's slow and delayed and everything. This is the word pixel where? The second line. What do you mean? Oh. Yeah. Okay, let's cheat. Or we do it different way. Wait. Write to PSRAM, write to PSRAM or verify. Here we go. At least we got any result. At this point, oh man, this is evil. How did I miss the clock in the document? So the document, let me check that. Yeah. Let me check that. CLK, but what CLK? Wait. CLK out. Okay, let's check. Output. The user logic design clock with a frequency of memory clock. Almond power. It doesn't say anything about that. Let me check. Clock rate is 1 to 2. Oh, look at that. You see, burst length, that's like byte. 16 bytes, 14 clocks. It's not that bad. That should be doable. Okay, you will find out next time. Reference input clock is usually okay. The user logic design clock with a frequency, it doesn't say anything about, whoops. Reset and in 16 bytes actually. In that case, it's words, I think, but the word size for that memory is 8 bits, the width. You can input chip working clock, which is generally a high, oh yeah, that's memory clock, PSRAM clock, PL memory clock, generally using clock. CLKD. It never says anything about the clock. Oh yeah, okay. Clock ratio. Interfaces connect the input reference clocks external. Reference design, okay. Okay. Wait. There's a reference design. Let's check that. Oh no, we are at the beginning again. Okay. Okay. My friends, that's all for today. I'm sorry it was a little bit dull, but here. I'm sorry it was a little bit dull. Unfortunately, that's the way it is always with debugging. It's 90% of the time. And I hope we can actually... I received a 100 megabit megabit ADC by next time, and we can use it with that thing. ADC. Yeah. Max, you didn't... I ordered the 100 mega samples ADC for the oscilloscope thingy. And we can start playing around with that. It will be more enjoyable. Oh, my battery is running out. I'm just in time. And angry data clocks. No. Okay, yeah. Analog digital converter. Good night, yeah. And I'll keep the update was so long in the beginning. Next time it will be most probably I will have some beamforming by next time. So see you next time. Bye. Thank you for joining, everyone. Have a good sleep. Good night. And now I just need to end. Sleep tight. Yeah. Here we go. Bye-bye.